Hey everyone, I want to keep talking about simple groups. In particular, I'd like to talk about finite simple groups and why the study of finite simple groups is key to the understanding of finite groups overall. So this will be kind of a bit of a historical lesson. So given a finite group capital G, and let's call it G is the group, but I want to refer to it as G0. Now it's possible we've got this finite group here. Maybe it's a simple group, maybe it's not. If it's not simple, so if G0 is not simple, that means that it has some normal subgroup that is not the identity and it's not all of G0. And so in particular, we can choose a maximal normal subgroup. So, so if G is not simple, choose a maximal normal subgroup. Let's call it G1. So G1 is a normal subgroup of G0. So now, okay, so what that tells us then is that the quotient G0 mod G1 is simple. And then maybe G1 is simple, maybe it's not. So we can say it like this. So then G0 mod G1 is simple. If G1 is not, so if G1 is not simple, we're going to just repeat this pattern. So if G1 is not simple, choose a maximal normal subgroup. G2. All right, so now we've got G2 normal in G1, and then we can keep going. So so then G1 mod G2 is simple, and then you can ask the question, is G2 simple, or if not, choose a maximal normal subgroup G3, and you continue this process, and eventually, continue this process until eventually we arrive at a simple group. So continue this process until, and we know that this process is going to terminate because G is finite, right? So continue, let's call it Gn. So continue this process until we arrive at, or until we obtain a simple group G sub n, that would be normal in G sub n minus 1. Oh, sorry. Yeah, that's right. That's right. Right, we would choose a maximal normal subgroup Gn sitting inside Gn minus 1, and in the final case, then it would turn out that this group would actually be simple. Okay, now what this does, this creates, or this leads to, or this, this gives us a composition series is what this is called. So composition series, and it will go like this. So we will have the trivial group, let's call that G sub n plus 1. Which will be a normal subgroup of Gn, which is normal in Gn minus 1. And this keeps going until eventually we get to G2 normal, that's fine, G2 normal in G1, normal in G0, which is G. Sorry, this is a little awkward here, but anyway, so we have this series right here, and I'm going to write right above it, so where each quotient Gi mod Gi plus 1 is simple. These quotients have a name. They're called, oh, let me underline this composition series. And these quotients here have a name. Those are called composition factors. So each quotient is a composition factor. Now, there's a famous theorem that tells us that up to ordering, the composition factors are actually unique. So essentially, there is one way to do this. When you start off with G, it's going to break up to ordering. It's going to break up into a situation, a composition series, or you will get a corresponding composition series, right? Where you have a bunch of composition factors. Each one of those are simple. Now why, where does the non-uniqueness come from? Well, it comes from the fact that one person might choose G1 to be this maximal normal subgroup, and somebody else might choose G1 to be a different one. And so then when you take the quotient, you actually get different. But up to ordering, you're going to get the same. All right, so this is called the Jordan-Holder theorem. Jordan-Holder theorem. And I'm just gonna paraphrase it. It's not important for our purposes. So the composition factors are unique up to ordering. Now, here's the thing, many of the properties, so many of the properties of G can be determined by the composition factors. And also, and here's maybe the really interesting thing. So, and G can, interpreted correctly, can be reconstructed from the composition factors. So what does that tell us then, right? If you know all the composition factors corresponding to a particular group, then you essentially know who that group is. And all of these composition factors are simple. So in a sense, the composition factors are the building blocks of the group G, and all of those are simple. So a way to interpret this is that for finite groups are built out of finite simple groups. Right? So let's say it like this. So finite simple groups are the building blocks of all finite groups. So mathematicians, they recognized this back in the early 1900s. They realized, oh, what we really need to do if we want to understand finite groups, what we need to understand are finite simple groups. Because if you knew who all the finite simple groups are, then in essence you would know who all the finite groups are. So that means then that the study of finite groups, in some sense, boils down to the study and classification of finite simple groups. And so, let's say this, so classification of finite simple groups. So this is one of the great undertakings, mathematical undertakings of the 20th century. So, yeah, let's say, yeah, one of the major mathematical projects, undertakings, I don't know what the right word is here, accomplishments maybe, of the 20th century. Now, one of the big pieces, this is called the Feit-Thompson theorem. And this is, let's see, when does this come out? 1960, I don't have the exact date. Somewhere in the 1960s is when they were doing this. So Feit-Thompson showed this. A non-abelian say this right. Right, so a non-abelian finite simple group has even order. Certainly not obvious. But what it's saying is if you have a non-abelian finite group of odd order, you are guaranteed it is not simple, right? There will be some non-trivial proper normal subgroup in there. Now, if you've ever looked at, let me see if I have it written down here. Oh yeah, I didn't say which journal. I think it's the Pacific Journal of Math, I believe, is where this result occurred. And so typically when you see a journal, if you look at mathematical journals, they come out, let's say, every quarter, sometimes every month, sometimes twice a year. And in a particular math journal, when it comes out, there'll be 8 or 10 articles in there, sometimes even more. And so a typical article is somewhere between 10 pages, 20 pages. Every once in a while you get a really long one that's about 50 pages. Sometimes they're even real short, like 3 pages. So typical journals, a journal issue when it comes out, has multiple articles written by different authors. This guy submitted this one, this guy submitted this one, and then, this theorem right here, the Feit-Thompson theorem, occupies the entire journal. Right? So this journal is dedicated to the proof of this one theorem. It's 255 pages long. So, so this is a big deal. All right, non-abelian finite simple group has even order. Took a lot of work. But what did it do? It essentially ruled out half of the groups. Right? If you're looking at finite groups of odd order, guaranteed, non-abelian, guaranteed, not simple. Now, for this work, so Thompson, for this work and others, he won the Fields Medal, which you probably have heard. I mean, sometimes people refer to this. There is no Nobel Prize for math, and so the Fields Medal really is, I don't know, maybe even bigger than getting a Fields Medal is at least equivalent to getting a Nobel Prize when it comes to math, right? That's the biggest prize out there. Now, let me just give you a kind of a quick rundown. So the classification goes like this. a finite simple group lies in one of 18 families. And we've seen a couple of these families, right? So let's say 18 families, including ZP, right? When P is prime, we know that the integers mod P, ZP is a simple group, right? So this gives us one infinite collection of simple groups. Another one, AN for, for n greater than or equal to 5. And then there's some other sort of fancy sounding ones that are named after people. Let me just give you a few of these. Chevrolet. So there are other collections of groups, Steinberg. And they continue on various subclasses of the overall collection of finite simple groups. So there is this collection of finite simple groups, and there's also, what am I saying? So if you have a finite simple group, it will lie in one of these special families, right? And there's a bunch of names of them. There are 18 of them. Or is one of the 26 what are called sporadic groups. And so there are these 26 groups that really just don't lie in any particular class. They're just special on their own. And so the classification says if you have a finite simple group, it is guaranteed to be one of these. It'll live in one of these families, one of the 18 families, or it'll be one of these oddball groups. And the sporadic groups culminate, so let's say culminating in what's called the monster group. All right, so there's this group out there called the monster group, and the elements, or let's say the monster group, whose elements are 196833, 196833 by 196833 matrices. Right, so this is a group consisting of matrices with 196833 rows and columns. The size of it, so let's call the monster group capital M. The size of M, right, the order of M is about, well, let's say approximately 8 times 10 to the 53. So it took a huge amount of work. The Feit-Thompson result was just one little piece of the puzzle. Saying in 1981, Gorenstein announces that the classification is complete. And then people realize, oh, there's a gap. Now, I mean, this is 10,000 pages that you have to weed through, right? To get all of the classification understood, all of these 18 families plus understanding the sporadic groups. About 10,000 pages. And at some point, someone discovered a gap. Oh, we missed something. And so then it took another while. And so in 2004, the final announcement, so Asch, A-S-C-H, Bacher, announced once again, so the classification is complete. And now what people are working on is, I don't know if they call it 2.0 classification. they are trying to streamline the classification, right? So that it's more easy. You know, it's not 10,000 pages long. I don't know exactly where they're at in the reclassification. So it's the same classification, but they've cut out a lot of the well, I don't know. I guess streamlined is the best way to say it. In your last homework assignment, you proved this, or this was one of the things that you're supposed to show. So if H is a subgroup of G and N is a normal subgroup of G, then Hn, which was the set of all things of the form little h times little n, where h is an element of capital H and n is an element of capital N, this is actually a subgroup of G. So for example, in S3, let's call capital H, it's going to be the subgroup generated by 1, 2, and N is going to be the subgroup generated by 1, 2, 3. S3 has 6 elements. This subgroup right here has 3. So N is a normal subgroup because it has index 2. And so then, so let's say note that N is a normal subgroup of S3. And so what do we have now? If we look at H times N, let's see what we're going to get. So in fact, and let me write out who these are. So H consists of the identity and the transposition 1, 2, and N consists of the identity and 1, 2, 3, and then 1, 2, 3 squared, which let me just make sure, 1, 2, 3 times 1, 2, 3. 1 goes to 2, which goes to 3. 3 goes to 1, which goes to 2. 2 goes to 3, which goes to 1. Yeah, so it's 1, 3, 2. Okay, so here's H and N, and if we look at H times N, what do we get? Well, we're going to get I, I'm going to multiply, so I'm going to have I times I. I'm going to have I, or I'm going to have 1, 2 times I, which will be 1, 2. Then I'm going to have I times 1, 2, 3, which is 1, 2, 3. I'll have I times 1, 3, 2. Then I will have 1, 2 times 1, 2, 3. And if you check, well, okay, let me write it out. So 1, 2, let's write who this is. So it's 1, 2 times 1, 2, 3. And then the last one, when I do 1, 2 times this piece, we'll get 1, 2 times 1, 3, 2. So what did I just do? I took the elements from H, multiplied them by the elements of N. Here's the 6 elements that we get. And if we write these out, then it'll be I, 1, 2, 1, 2, 3, 1, 3, 2. And you can check. All right, so let's see, who is this one? 1 goes to 2, which goes to 1. Okay, so that stays fixed. 2 goes to 3. And 3 goes to 1, which goes back to 2. And then what do you think is going to happen here when you multiply this one? Let's see, so 1 goes to 3. 3 goes to 2, which goes to 1. And then 2 goes to 1, which goes back to 2. So notice what we get. We got all of S3. So in this case, with this choice of H and this choice of N, when we look at H times N, we get all of S3. And so that's nice. That's useful, because what it does is it tells us that everybody in our group can be expressed as somebody from here times somebody from here. It gives us a way to decompose the elements into an element from a group here, and an element here, or a subgroup here, and a normal subgroup here. Let's look at another example. So in Z, let H equal 2Z and N equal 3Z. Of course, and in fact, every subgroup of Z is normal, but here I'm going to choose H to be 2Z, N equal to 3Z. And then if we write H times N, it really makes more sense to write H plus N. But I'll write it as H times N. But who's that going to be? It's going to be everything of the form 2x plus 3y, where x is in 2z, and no, where x is in z, or well, x and y are in z. Right? What you would have is a multiple of 2 plus a multiple of 3. And I'm going to use plus because that is the operation when you're working inside Z. And notice, that's equal to Z right there. And so here's a way to think of all integers, right? There's various ways to think of integers. One way to think of them, every integer can be expressed as 2 times an integer plus 3 times an integer. So here's the point why we like this. So when G is equal to H times N, then every element, say X in G, can be expressed, decomposed as X equals little h times little n. Now, so that's going to be useful, but the problem is such an expression may not be unique. So we'll say, but this expression may not be unique. So for example, in our last example right here, what do I have? Oh yeah, 1 can be written as -2 plus 3. It can also be written as -8 plus 9, right? That's 2 different ways to express 1, right, using this decomposition right there. Right, so uniqueness, it's preferable when you have a unique expression so that everybody can be expressed uniquely in this way. And so this next definition is going to capture what we need to get uniqueness. So, a group G is D. Yeah, D. The internal direct product of H and N. Remember, back when we were learning about direct products, G cross H, I said, well, okay, this is really the external direct product, and there's such a thing as an internal direct product. So here we are, we're learning about that now. So it's the internal direct product of, and actually let me be a little bit more specific here, of the subgroups H and N if. So 3 things need to happen here. Let's put them up here. So part A, H is a normal subgroup of G, and N is a normal subgroup of G. Part B, G is equal to Hn, and C, H intersect N is trivial. So if those 3 things occur, then we say that G is the internal direct product of these two subgroups. And the notation when this occurs. We would write G equals H cross N. And you should say, oh, that's terrible. That's the same notation we had before. Here's the idea. Here's the reason why this notation is used in both the internal and external direct product settings. Oh, and I should say, in the abelian case, it's usually written G equals H plus N, circle plus, so this is in the abelian case. So here's the idea. Let me just give you a quick sketch of why the same notation is used. In the external direct product, what you have is all the elements of G can be written, and let's say all the elements of, let's come up with, I don't know, G cross H, I guess. Everybody can be written as an ordered pair G comma H. In the internal setting, everybody can be written as, I guess I got to use an H times N. So the idea is, and I know I'm using different symbols here, I've got a G comma H here, I've got an H times N here, but the idea is passing between these two, and we'll see that these really are these are one and the same. The idea is that passing from here to here is essentially inserting a comma or deleting a comma. Right? So maybe I'm saying too much right now, but we'll see. We're going to get a theorem in a second that will explain this. Yeah. Okay. Here's a quick example. So in Z6, let H consist of 0, 2, 4. Right, so that's the subgroup generated by 2. And N is going to be 0 and 3. 0 together with 3. And that's the subgroup generated by 3. So now, so notice, of course, because Z6 is abelian, H is normal in Z6, N is normal in Z6. The intersection, so H intersect N, consists of just the trivial elements, so just 0. And so Z6, you can check. Well, in fact, let's write it out like this. Hn is going to be all possible products that you can form. So let's do this quickly. 0 times 0 is 0. 0 times 3 is 0. 2 times 0 is 0. 2 times 3 is... Wait, what am I doing? Oh, sorry, I'm sorry, I just started multiplying. Sorry, I just went crazy there. I should be adding. The operation is addition mod 6. So 0 plus 0 is 0. 0 plus 3 is 3. 2 plus 0 is 2. 2 plus 3 is 5. 4 plus 0 is 4. 4 plus 3 is 7. Mod 6 is 1. And so what we see then, so we can say therefore, Z6 is the internal direct product of these subgroups and because it's abelian, we would write it like this, right? So it's the internal product of those two subgroups. Okay, and here's the theorem that we need. So So let's let let's get a couple of normal subgroups. So let's let H be normal in G, and N be normal in G. Then G is the internal direct product, H cross N, if and only if each X in G has a unique expression as X equals Hn, where little h is in capital H and N is in capital N. All right, so this theorem gives us exactly what we need. It allows us to decide when we get unique expressions, and it's exactly the 3 items that we had in our previous definition. Okay, so in the forward direction, so we're going to assume that we have an internal direct product, so G is equal to H cross N, and we need to show that uniqueness of expressions occurs. So let's assume that G equals H cross N. Okay, so what does that mean? So then G equals Hn, and H times N. All right, that's part of the definition. And so for each little x in G, there exists a little h in capital H, a little n in capital N, such that x is equal to little h times little n. And so we want to show uniqueness, so we're going to say, suppose we have some other expression. So suppose x is equal to, let's say, h bar times n bar for some h bar in capital H and n bar in capital N. All right, so what does that mean? So then, well, it means that Hn is equal to h bar n bar. And so if we invert things, and so let's see, I'm going to hit on the left-hand side by h bar inverse. So we'll have an h bar inverse h equals, I'm going to hit on the right-hand side by n inverse. So we'll have n bar n inverse. Now, where does this live? Well, this lives in H, and it's equal to something that lives in N, which means that this has to live in the intersection. So this lives in H intersect N, which by assumption is trivial. So what does that tell us? It tells us that H bar inverse times H is the identity. It tells us that N bar times N inverse is the identity. So we can say thus, H equals H bar and N equals N bar. All right, so that tells us that we have unique expressions. All right, now for the reverse direction. So let's assume every x in G can be expressed uniquely as x equals hn, where little h is in capital H and little n is in capital N. Okay, so now what I need to do is show that G is the internal direct product of H and N. So this implies that G equals H times N, right? Everybody can be expressed as somebody from H times somebody in N. Now we need to show that they are normal. Oh, I'm sorry. We assumed they're normal. Never mind. I need to show that the intersection is trivial. So now suppose let's say x is in the intersection. So H intersect N. Yeah, okay, sorry, I got spaced out there for a second. So suppose x is in H intersect N. So then, there exists H in capital H and N in capital N, such that what am I doing? Yeah, such that x equals H and x equals N. So now E equals E times E. I could write this the other way. E times E equals E, which equals H inverse times N. And so, by our uniqueness assumption, what does it tell us? It tells us that H inverse equals E and N equals E, right? The H inverse has to equal E and the N has to equal E by uniqueness of expressions. Therefore, X is equal to the identity, and we conclude that H intersect N is trivial. Okay, so that completes the proof. And so now we have this way of understanding why we might care about this internal direct product idea, right? Every element can be expressed uniquely as something from one group times something from another group. And this should remind you of, in vector spaces, what a basis is, right? A basis is a unique way of expressing elements in a vector space in terms of some small group, some small group of building blocks, if you like. And so here's another idea, or here you can see this idea mimicked in the group setting, right? Each element can be expressed in terms of a couple of subgroups. So you can think of the elements of the subgroups as the building blocks. Right, so it gives you a way to decompose. I think, well, I got office hours about to start right now, so we will see you next time.